All right, everyone, welcome back. And in this video, we're going to pick off where we left off in the previous video, the problem set video. And so what we're going to talk about is we're going to take the exponential laws further, right? And so that means talking about generalized negative powers, right? Which basically means we're going to talk about, how to deal with things like maybe x to the negative 3, not just x to the negative 1. We touched on this a little bit in the problem set, but I'm going to formally define it here in a general case, as I said above. And then the next thing we're going to talk about, which I touched on in the end of last video, was like roots, not just square roots, but like the third root, the fourth root, the nth root, where n is any number, and what that means, and then how to translate that into fractional exponents. And then, of course, applying the laws we discussed to problems with fractional exponents, with more generalized negative exponents, and so on. Okay, so let's get started by talking about how to generalize negative exponents. And it's really quite simple. All we need to do is use law 2, right? And it's a little bit of a clever manipulation, right? We just got to make sure it makes sense, right? So if we look at n to the negative 1, right? We know from the first video on this topic, the Law of Exponents introductional video, that this is just 1 over n, right? And so here n could be any number, right? And so based on that, the fact that n could be any number, right, or any term for that matter that represents a number, we can name n something. We can name n x to the n. Let's call n x to the n, right? No, we don't want to use n in both cases. Let's call n x to the k, where k is some other number. So we know n is equal to x to the k. Okay. Okay, so let's plug x to the k back in for n to this equation. So that means x to the k to the negative 1, right, we're the whole thing to the negative 1, is equal to 1 over, again, there's an n here, x to the k, right? Great. And so we know that that second law of exponents tells us that we can multiply out powers when they're in a parenthetical format like this. So we can actually go ahead and multiply those together. And so what that's going to give us, let me erase this definition here. All that's going to give us, if I erase the whole thing, right, it's going to tell us that x to the negative k is equal to 1 over x to the k. Great. And so what we've done here is we've successfully essentially turned n to the negative 1 equals 1 over n into an expression that deals with, an expression, right, that allows k to be any number, right? And so this expression allows, now we can basically essentially say k, okay, k doesn't necessarily just have to be 1. We can have x to the negative 2 equals 1 over x squared, right? Not just x to the negative 1 equals 1 over x, right? And so now, okay, yeah, we can basically say, well, now we can talk about all negative powers for any number, any variable, right? Which is great. And this expression is extremely important, right? So if I was like, okay, what's 5 to the negative 3, right? Well, that's just 1 over 5 cubed, right? Which is 1 over 125. It's not always necessary. All right, but this is the first key law I wanted to introduce in this video, with a short proof, right? Great. Okay, so now that we talked about generalized negative powers, let's talk about roots and fractional exponents. Great. Okay, so a lot of you guys are probably familiar with square roots. It's very commonly talked about, right? And I touched on this a bit in the problem set, but if you haven't seen that, I'm going to talk about it now. Right, where the square root of x, right? The definition basically is that the square root of x times the square root of x, where there's two times the multiple of square root of x is equal to x, right? That's what it is, right? Okay, so with this in mind, right, how can we convert square root of x to something, where x is to some power, right? So how can we convert the definition of square root of x into an x raised to some power, u, let's call it, right? Okay. So we can say, if we let x to the u equal square root of x, then, by definition, x to the u times x to the u equals x, and we'll call it x to the first here, because that's just x. That's going to make our life a little bit easier, right? And then we can apply the first law. I'll use a different color for this, because if you notice, well, same base, right, and same power. That's not a condition for this to work, but we can use the law here, and we'll get x to the 2u is equal to x to the first. Right, great. You can all see that. Great. Okay, I'm going to erase this. So now we've made it this far. We've shown that x to the 2u is equal to x to the first. Great. Perfect. And so given that, we know x to the 2u is equal to x to the first. That's great. I'm going to write that in green here. Well, that means that 2u has to equal 1, right? Because in order for these expressions to be equal, their powers also have to be equal, since the bases are equal, right? That's kind of a logical leap I'm making here, right? So we could set 2u equal to 1. And by the way, we'll formally talk about why this is true and how we can use it to solve equations in a chapter involving something called a logarithm, but you don't have to worry about that right now. Right, so now all we have to do is solve this single line equation, right? We divide both sides by 2, and we get u is equal to 1/2. Okay, this is a pretty big deal. I'm going to erase this now. And now that we know u is equal to 1/2, I'm also going to erase this top here. Now that we know u is equal to 1/2, we can formalize what we just talked about. We now have a way to represent the square root of x as something to an exponential power. In this case, it turns out to be fractional, right? We know that the square root of x times the square root of x equals 1. And since u is equal to 1/2, right, x to the 1/2 times x to the 1/2 equals 1. And we notice both these are the same number. Two of the same numbers multiply together to give us x, right? Sorry, that's an x, that's an x. And in the first case, two of the same numbers multiply together to give us x. This x to the 1/2 is equal to the square root of x. They both satisfy the same exact definition, right? That's a really important fact. Okay, so now we basically, as I said in the topics, we've introduced the idea of a fractional exponent, right? And what that means, right? So x to the 1/2 is our first example of a fractional exponent. In this case, x to the 1/2 is the square root of x, right? And what we'll see here, as we talk about things like, and I mentioned this in the problem set, the last video I made, the problem set for laws of exponents, x to the 1/3 is equal to something, right? X to the 1/4 is equal to something. And these all involve something called the concept, these all involve roots, right? These expressions, these fractional power expressions, are all related to the roots of a number, like the square root. We'll talk about the third root, the fourth root, right? Things like this. They're essentially numbers that when multiplied by themselves n times will give a number x, right? They're roots of a number. So that's what I'm going to formalize now, right? So what is the root of a number, right? And how does it relate to these really nice fractional exponents that are going to come in handy when we solve more complex problems, right? Because that's really the reason to learn them, right? Okay, so we know the square root of x is the number when multiplied by itself twice equals x, equals some number x. It could be a, it could be k. I'm calling it x because x is very common, it's very useful. We denote this with this sign. The thing is, when we move to things like the third root of x, we actually have to put a little 3 up here to signify that it's the third root of x, is not the square root of x. And the third root of x, as you may have guessed, when multiplied by itself 3 times, it's the third root, will give us x again. Now, if we continue this pattern, the fifth root of x, when multiplied out by itself 5 times, just like that, we can denote that with a 5, will give us x, right? And we can generalize this, okay, to the nth root of x, right? Where n is some arbitrary number. When multiplied out by itself, n times will give us x, right? So with that in mind, we can create kind of a general expression for what the nth root of x is as a fractional exponent. And that's what we're going to get to now, right? So this is n times. Perfect. Great. I'm going to erase this, but this is something definitely worthwhile noting if you're unfamiliar with this topic, because it's going to show up. It shows up in many different other areas of math. Right? Okay, so we know the square root of x is x to the 1/2. So what about the third root of x? Let's take a look at the next step up from that. Well, I'm going to tell you right now it equals x to the 1/3. And let's see why. We can prove it similarly, or we can do, kind of observe this by inspection, right? But if I multiply the third root of x by itself 3 times, I'll get x. And similarly, if I multiply x to the 1/3 by itself 3 times, right, I'll get x. So these both satisfy the same property, much like our example with the square root of 2, right? And so essentially what this is saying, right, we could talk about this for the nth root of x, right, is if I have some number n, right, and I'm multiplying it out by itself n times, right, I'm getting x, right? So we can say, okay, the nth root of x, right, is equal to x to the u, right? So it's some number that's multiplied by itself out many times, right? N times to get x. And it could be any number. It could be a small number times. It could be a large number times. But let's say the nth root of x, just like in the square root of x case, is equal to x to the u, where u is some other number. I'm using it as a placeholder here. We're going to solve for it in kind of a little bit more of an atypical equation than maybe you're used to seeing, but it should make sense, right? If it doesn't make sense, feel free to watch this part multiple times or leave a comment. Great, so what we're going to end up doing is we're going to say, okay, the nth root of x is x to the u. Okay, so what can we do with that? Let me use a different color for this. We can say that x to the u times x to the u, right? Times x to the u. Again, n times equals x. Great, okay. So let's think about this. Since this number is n, that's a key point in this problem. Okay, so if we apply that first law of exponents, we get x to the power of u plus u. So erase that n here, put that on the top here. There's n times being multiplied out, n times. Plus, so we get, essentially, when we consolidate this with law 1, we get x to the u, right? Again, out n times, because originally we had n terms, right? Which means we can write this as x to the power of nu, right? Because we're multiplying u out, we're adding u to itself out n times, since there's going to be n terms here, right? It's a bit of an abstract leap, but that's how we're going to find out what n is actually equal to in the general case, right? Great. So again, this is x to the nu, like we just stated, equals x to the first, right? And just like in square root of x, since these bases are the same, right, this power has to be the same for these to be equal. And so we can set nu equal to 1, right? And then this is just, again, a bit of a trickier equation, but we still want to solve for u, right? So we divide both sides by n, which gives us the result that u is equal to 1 over n. And that's fantastic because we've now generalized the nth root of x. In fact, we now know, based on the fact that u is equal to 1 over n, that the nth root of x, for any number n, fractional or not, whatever, it could be any number, the nth root of x is equal to x to the 1 over n. We just proved that, right, mathematically. That's a very, very important result. So now I can say, okay, the fifth root of x is definitively equal to x to the 1/5 because I proved it for n. That's the power of proving it for a random number. You can now say it's true for every number. That's called induction. It's not nearly as important as this concept, but it's, you know, if you're interested in this, it's definitely important to note, right? Great. So that's basically what a root exponential is. Now we're equipped to deal with these things in a logical manner, right? So if I asked you, for example, what's x to the 1/5? In a root form, you would simply say, okay, the definition, the nth root of x is x to the 1 over x, x to the 1 over n. So this is equal to the fifth root of x. And of course, it satisfied that property that the fifth root of x multiplied out by itself 5 times, n equals 5 in this case, will give us x. Perfect. Okay. Similarly, and a little trickier, right? You have to recall those two definitions. What if I asked you about x to the negative 1/5? Right? We can do this, right? Because we've defined an x to the negative n before, right? Okay, so x to the negative 1/5. Well, first we'd have to rewrite that as 1 over x to the 1/5, just like that law states. X to the k is equal to 1 over x to the k, right? X to the negative k, right? Great. So that's the first step, right? Because we can't have a negative 1/5 root of a number, right? It's not possible, right? That's the key logical leap we have to make. That we can't have a negative 1/5 root of a number, right? How is that possible? You can't have a number that multiplies by itself negative 1/5 times. Does that make any sense to you? It doesn't make any sense to me. It is, you know, in higher level math may be true, but in this case, right, this is how we rewrite it first, and then secondly, we'd have to say, okay, this is 1 over the fifth root of x, right? And that's perfectly fine. That would be the acceptable answer here, right? Great. And similarly, we can now, you know, we can deal with any fractional exponent. It doesn't have to just be x to the 1 over k. And the reason for that is, okay, now we can say we have x to the 1 over k, and we can apply our second law of exponents to it. All right, all we have to do is apply our second law of exponents. Great. So the second law here would mean that we can multiply this by some number m, right? Great. So now we could have an expression where it's equal to x to the m over k, right? This is perfectly legitimate. All I've done is substitute in this new number that we've just learned about. So for example, I could figure out, okay, what is x to the 1/5 squared, right? Well, by that second law of exponents, which again still applies to these numbers, it's x to the 2/5. It's kind of great, right? Now I can deal with any fractional power in a very nice way. And if I was asked, the next leap here is, okay, how do I find this in a root-like form, right? That's the key here. How do I find this as a root, right? Well, what I can do is I can write this as the square root of x squared to the 5th. And the reason I can do this, well, actually, let's not go there quite yet. My point is now that you can rewrite these things in nice fractional exponential patterns, right? We can now deal with these in a nice way. So at this point of the video, I'm going to kind of do a recap of all the stuff we've covered up to this point with laws of exponents. I'm not going to rewrite the 3 laws because I'm fairly confident, and I would hope that you have them memorized by now. If you want a refresher on those, they're in the first video, right? So topics would be 1 is the first 3 laws. 2, negative exponents. 3, fractional exponents. 4, great. So that's what we covered so far, right? So just to recap, 3 laws of exponents, negative exponents, fractional exponents, and roots, the nth root of x, right? So that's all we've covered essentially up to this point, right? Great. All right. So let's erase this, talk about some of the last topics, and we'll discuss some of the last topics in kind of exponents and what they mean, right? Okay. So the next kind of challenge in this, the next concept in this, segment is going to be generalizing x to the m over k, right? And so all that means is we're going to be talking about how x to the m over k can appear in root-like forms. So we know, with x to m over k, but we know that x to the 1 over k is the kth root of x. That means the k is in the little corner there, right? We know that, right? Now the question here is if we know this identity to be true, right? So if we have x to the m, right? And we take the kth root of x to the m, right? Based on this logic, we're taking the kth root of x. In this case, this would be, we can take the kth root of u, right? This would be x to the u over k, right? So this is kind of the next leap I want to talk about in this segment, is kind of how to generalize these sorts of things, right? Perfect. Let me think about the best way to say this. So x to the 1 over k, we'd have the kth root of u. Great. So the question is, what happens if I take the kth root of x to the m? Not just x to any power, x to the m. How can I write this in a root-like form? So I'm going to take the kth root, right? And if I take the kth root, then all I'm doing is I'm taking x to the m to the 1 over kth power, right? That's all I'm doing. I'm just saying x to the m is my x in this case, right? I'm taking that to the 1 over kth power, right? So that's all I'm doing. So this is another powerful general expression. We're saying the kth root, it's another important identity, kind of the last one in this video, is equal to x to the m over k, right? And so what this means, based on that, we can just take that x to the m to mean the x in this case, and we can apply that second law of exponents there. We can take this to mean, right, now basically a way to deal with any, fractional exponent and convert it into a square root. So this is one of the more important concepts, right? Say I had we'll call it z to the 2/7, right? And I want to say, okay, what's this in a root like as a root, right? Right. Okay, well I can say, okay, my m in this case is 2, and my k in this case is 7. So I'm taking the 7th root of z squared, right? That's a way to write it in a root-like format, right? Based on this, sort of manipulation. Okay, we can say x is some number to the power of x, right? Because x is just representing some number. And so we can use that fact to further generalize this statement, right? So we could also go on the inverse. You could be asked, for example, okay, they're giving you some expression x to the they could say, we're giving you this expression and we want you to go in the reverse. X to the 27th, and this is a 3, right? What is this? The third root of x to the 27th, right? This is just x to the 27th over 3, right? Which is x to the 9th, right? So that's quite a nice way to simplify this, right? That's kind of the way to think about it, right? So as a recap with this part, right? All we did here, so I want to make this clear because it's a bit tricky. This one especially. So we took the kth root of u. Let's call it u, which is u to the 1 over k, and then we just let u is equal to x to the m, right? So then we said the kth root of x to the m is equal to x to the m, right? To the power of 1 over k. Then we applied the second law there, and we got this nice expression, this nice identity, if you will. Great. So now let's wrap this up. Let's do one practice problem just to kind of sum it up, to kind of generalize, talk about all the laws of exponents, right? Great. Perfect. So this practice problem is going to have some fractional exponents in it. It's going to have some nice things going on in it, right? Just some good practice. We'll have a denominator here. We can talk about negative exponents of anything, right? Because we've discussed basically all the different variety here. And again, after this video, I will do another problem set on these topics, right? Just to clarify, I'll do 5 problems of varying difficulty, right? Maybe some new ideas, maybe some old ones, right? Same idea there, right? Let's have z to the 1/3 times z to the negative 1/4. It's a little tricky. Times k cubed to the 1/7. That's being divided by x times 1/4 to the negative 1. It's very tricky. It looks very tricky. It's not very tricky if you understand how to apply the laws, right? So that's what we're going to do here. Great. Practice problem number 1. First, let's take a look at these two z's, right? Remember, our first law of exponents can be applied to any number, right? And they have the same base, so we can go ahead and simplify these, right? Bring them down here. It's just z to the 1/3 minus, again, we're adding them, so the minus sign won't change, minus 1/4. We give these a common denominator. Then we get 1/3 minus 1/4, which is just 4 minus 1, 4 minus 3 will give us something, z to the 1/12. Right, great. So we've managed to simplify that first part there. That's just z to the 1/12. I'm going to erase this, but we now know what that is. Great. Times this part right here. That's just k cubed to the 1/7. Again, all we need to do is apply that second law of exponents. That's 1/7. We multiplied that by 3 when we multiply two fractions, a fraction and a number. We're just multiplying them top and bottom, right? So that gives us k to the 3/7. Perfect. So now we have z to the 12th times k to the 3/7, right? We just clean up that whole top, right? And then on the bottom here, the x, nothing's going to happen to it, right? So we can just divide by x. And then the last part we have to address is this 1/4 to the negative 1, right? So all that's going to give us, right? 1/4 to the negative 1. Well, here's the question. What's 1/4? All 1/4 is 4 to the negative 1. So really all this is 4 to the negative 1 to the negative 1, right? We apply that second law. See, these two cancel out. They give us a positive 1. That means this is just 4. And we can take that 4 and slap it right in front of the x, right? So now we have our final answer, right? We took the whole simplification out. We can now write a final answer of z to the 1/12 times k to the 3/7 all over 4x. Perfect. And then as a bonus question, can you write this in a root form? Can you convert z to the 1/12 to a square root like shape? Can you convert, not a square root, like a root? Can you convert z to the 1/12 into a root? Can you convert k to the 3/7 into a root? Those are the questions, basically, that might be good for practice. In the next video, of course, I will talk about, I will do some practice problems, right? So just as a last note here, and I'll leave this up here. From the last section, x to the m over k is equal to the kth root of x to the m, right? Last thing to remember, great. Note it down if you need to. Make sure to commit that to memory. And I will see you guys in the next video, the problem set. Great.